Go to full screen, I hope. Now, let me clarify a couple of points on the previous recording, which was the first time through in using Fourier transform to solve boundary value problems. One thing I wanted to go through was any of these derivations, like these derivations, if you want more on that, ask me, email me, and I can send you a document. The second thing, I'm not sure it was clear. When I got to this initial condition, we have to take Fourier transform of initial conditions. In this case, that's this function. So the Fourier transform of this initial condition, Fourier transform of this f of x. It is also, since that's x there and it's 0 where t goes, the Fourier transform with respect to x is this u of alpha t, so that the Fourier transform of this guy is this big U evaluated at t equals 0. So this, which is u of alpha 0, which made this part just equal a. U of alpha 0 just equals a. That's on the left side here. And on the right side is the Fourier transform of this function, which we did in another recording. That's where you get the right side. Those are the two things we're equating. This guy evaluated at 0, and this guy's Fourier transform. Okay, here's what I would say. You have 6 ways. You have 2 variables and 3 different transforms, which gives you 6 permutations of what transform to use over what variable. First, you're always going to take the transform of a variable that shows up as a second derivative. It shows up as a first derivative, that's not what we're going to do. If the range of that, let's say you have a function of x and y. So if we have the second partial of u with respect to x, then that makes x a candidate for what we take it with respect to. And if the range of that x is minus infinity to infinity, it's a infinite range, not a semi-infinite range. If it's an infinite range, you'll use the Fourier transform. If it's a semi-infinite range, meaning from 0 to infinity, then you're either going to use the cosine transform or the sine transform. Then it gets into what was the initial condition. Remember, we're pretending it's with respect to x here. If the initial condition on x, the function at x equals 0, is just the function itself, use the sine transform. If it's the derivative or the partial derivative of the function with respect to that variable, you use the cosine transform. I allowed my students to put this on a formula sheet, and I told them if it got more complicated than that, I would give them a hint. Let's do another example. First, this is easy of which variable we're going to use because x shows up as a second derivative and t only a first. So that right there gives it away in this case. We're going to take it with respect to x. And since its range is infinite for the entire real line, we're going to use the Fourier transform, full Fourier transform. This is pretty much like the one we just did, except we have a different initial condition. So we take Fourier transform of each term, term by term. So k, and then Fourier transform of this second derivative, go back to the formula sheet, and it's this guy. On the right, excuse me, since it's just derivative of big U with respect to, that's all for the formula sheet. Excuse me again. Rearrange this, get everything on one side of the equation. I guess I bring what's on the left over to the right. And set it equal to 0. And I get the same familiar ordinary differential equation. And we know its general solution. So here is the format or the general solution of the Fourier transform of the answer. Not the answer, but the Fourier transform. Now we also have to work on the initial condition. So the Fourier transform of that initial condition is u of x at 0 means Fourier transform of this guy. That equals this big U where t equals 0, which is just going to be a. So big A equals the Fourier transform of this function. So now, which is this. So now we have to take the Fourier transform. So from here to here is all taking a Fourier transform of this function. Absolute value, we have to break up the integral. And we can add exponents. These are integrals you can take without resorting to a table. X-type integrals, we can do those. Or add them together over a common denominator. That tells us what the A is, because A equals that Fourier transform. Now we have what the answer, the Fourier transform of the answer. Now we have to go and take inverse Fourier transform. So we take our answer and put it in the formula for the inverse Fourier transform. Here is our answer. We have to keep simplifying it because we don't want any complex stuff in. So we use Euler's formula again. This is very much like the previous example. Place this e to the minus I alpha x with this for Euler's formula. Spread things out. Again, we have one part that's all imaginary, or the imaginary part. We'll make sure things are even. Cosine, remember, it's with respect to alpha. Cosine is even. Alpha to the 0, alpha to the squared, we have even plus an even, it's still even. Even over even is even. Alpha squared here, another even. Even times even, this whole thing is even. Here it's even down here, even here, but the sign is odd. So this whole thing is odd, it will become 0. Here's the only part that contributes. This is our answer, but we can simplify it because it is even and change the lower limit to 0. We have to multiply by 2 when we do that. So there is the answer to that. That was again using the Fourier transform, very similar to what we just did. I'll do this example 2 in another recording.